think this is a fairly common question, and some recent questions that we've got kind of hinge on this, because I noticed there's another presentation later today, so hopefully between the two of us we can answer some of your questions about why would you use drones for surveying and how do they really apply to GIS. Okay, so right, the goal is creating some awesome data products. What you're looking at here is a Z-enabled point cloud that was generated, through photogrammetry, through post-processing software that we use is Esri's Drone to Map, and it's an awesome platform, but it's almost too user-friendly, right? You're able to, put your drone up in the air, use a prescribed flight plan. There's a lot of controls for editing your area of interest as well as the type of collection. What is going on here? Sorry about that if some audio is coming through. But so a basic overview of what I do for our survey collection, basically have shifted to a 30-degree gimbal angle. We use SiteScan LE, which is limited edition for pre-flight planning, and it gives you some pretty nice metrics as far as helping you estimate the end data product resolution, as well as number of images it's going to capture, number of batteries to expect, etc. It takes a lot of the guesswork out of it, and I highly recommend using some sort of pre-flight planning software. Ground Station Pro is another awesome product that I've used as well. So the end result is basically just a bunch of images, right? There's some fancy ways of symbolizing everything, and you're able to, enable or disable some images if you notice that there's some corruption. But basically, the post-processing software, Drone to Map, is just taking a bunch of stills that have some basic georeferencing, creating a bunch of tie points, taking into account your ground control points, and then creating some pretty cool data products that we're going to get into in a minute. The ground control is something that really drastically improves the accuracy of your products. The difference between an aerial survey with and without ground control points isn't really the focus of my presentation, but I will note that with ground control points, especially survey grade, you basically get accuracies that are a function of the resolution of your end data. So for example, if you're outputting 1-inch resolution imagery, then you probably get a factor of 2 or 4x accuracy in your X, Y, and Z planes. So you can expect around 4 inches or maybe 6 inches relative accuracy, or absolute accuracy, sorry. We generally go for 5 to 10 ground control points per area of interest or per project. Launching from a ground control point so you can adjust the image altitudes is kind of a handy pointer. It just allows you to get a more accurate elevation product. So the goal is, these data products will get really high resolution ortho imagery as well as terrain products, so raster products such as a digital terrain model, a digital surface model being, taking into account any surface level terrain fluctuations such as vegetation, cars, buildings, etc. And then the DTM, which is specific to photogrammetry derived. It models the underlying terrain. However, we don't have LiDAR, right? So it's applying some algorithmic smoothing to the vegetation areas. And then, like I showed earlier, we can generate a point cloud, and this is computed from a lot of the image tie points, and then runs a densification process. This is a pretty detailed area, and was flown with that crosshatch pattern that I noted above that definitely allows you to capture those flat vertical surfaces as well. I've tried to run this model without any noise reduction or smoothing, so that's why you've got, you can see the power poles, the telecom poles, as well as some tree artifacts in here. But there's really no way to keep it from, oops, sorry about that, to keep it from smoothing. And that's one of my complaints of Drone to Map is the algorithmic smoothing is kind of enabled no matter what. So let's get into this comparison that I ran for the presentation. Here in Idaho, the Idaho LiDAR Consortium provides a lot of, a lot of awesome LiDAR data. And having flown a recent project in the area, I was able to collect some LiDAR-derived bare earth DEM for an area of interest that I'd also flown the drone, done a drone survey with. And so this provided kind of opportunity to do a cool comparison against some LiDAR-derived data products, which are kind of, the benchmark or standard against other products such as, my UAS survey that everything is compared against. I basically just had to go in and select some tiles. The download process was pretty easy, and the result is what we've got here, which is a bare earth raster. So this is basically an area about 150 acres, shown a little bit more just because of the clipping here, but it provided, I was able to get perfect overlap between my area of interest with my drone survey. So one of the first things that I did was just take my digital terrain model, my drone's DEM approximation, and just run a difference calculation, right? So just subtracted the bare earth model, or the digital terrain model value, raster values from bare earth values, and then symbolized them here. So red being areas where the bare earth model was higher, blue being areas where the bare earth model was lower. And then I've got a histogram here, and it basically shows, a general approximation of the overlap between the digital terrain model and my bare earth raster. Some things to pay attention to. I mean, the mean is really close to 0, so that's awesome. It means that we're not really seeing a huge skew between the DTM and the bare earth raster. There's areas of fluctuation. However, there's not like a noticeable shift, positive or negative. Standard deviation of 1.3. I mean, that basically means that the majority of the pixels are within, 1 foot, 1.3 feet. And so for an area this size with a lot of, vegetation, this was flown in early summer, I think that's pretty good. So that's basically a normal distribution, right? We've got a standard deviation that's close to 1 and a mean that's close to 0. That's good. And actually, the variations are, it's pointed to, right, we've got high variations in localized places, such as, these water areas, and then also these densely vegetated areas you can see here. Water was generally underestimated, and then these densely vegetated areas are, kind of overestimated. And that's a factor of, the smoothing that my drone to map processing software is applying, right? It's just not able to take into account, or really doesn't know what to do when you've got these densely vegetated areas. It actually does quite a bit better with flat vertical surfaces, right? Because it's able to identify those as man-made structures of development and raise them, RAZE, so just knock them down to the surrounding ground levels. So I also ran a couple of terrain profiles just to get a look at, the difference between the smoothness and the interpolation or extrapolation that the DTM has. This is crossing the river in the area of interest. So the LiDAR, the bare earth model derived from LiDAR, right? It's not getting any returns from the water. So it's basically just flat. There is no noise there. However, the DTM that's photogrammetry derived is still mapping the surface of the water essentially. And given the reflectiveness of water at certain places, and then it can vary between bright and dark depending on if there's a reflection or not. There's a pretty high degree of noise in here. So that's one takeaway that I'll highlight later on as well, is just the relative and absolute inaccuracy of these photogrammetry derived elevation products for areas that are covered in water. Another one here is, right, this is again crossing a little drainage down in the valley here. I was actually surprised at how much smoother the digital terrain model profile was. But you can see, it's running a smoothing algorithm, and so it's essentially it's underfitting a little bit here. You can see that it's overcompensated for what it sees as some terrain, but it's actually some vegetation, and then it's just smoothed it out and rounded it over this point. Kind of an interesting thing to notice that it's extrapolated outside of the range, and actually made it higher than what it found. And then also just noticing, in the upper right here and lower right, the high degree of variation in the bare earth LiDAR, these little, minute terrain variations, and then it's been smoothed out a bit again in the digital terrain model profile. And if we have time, I'll pop open ArcGIS Pro. We can look at a couple more as well. So I think I'm doing all right on time, but one of the other analyses that I ran is classified the area of interest just using a supervised classification tool in ArcGIS Pro, and then did a little bit of manual cleanup so that we could identify these developed or built man-made areas that are buildings, and clean up some of the water. And then from there, I was able to just generate a bunch of random points across the area of interest, and then extract the difference value, right? So the comparison between the digital terrain model and the bare earth model, and then also the land cover classification. And then from there, I was able to generate a number of different statistics. So let's open up Pro and just look at what that looks like real quick. So these are my random points. This is 10,000 points across about 150 acres. So pretty good distribution. And if I turn these off, you'll get a better sense of what's going on here. Again, you can still see I've got my my difference raster symbolized here. So values in red are where the bare earth LiDAR was higher. Values in blue is where the bare earth LiDAR was LiDAR derived product was lower. I've got a couple ground control points just left over from my drone survey there for reference. And if I turn on, this is my classified raster. So I think this is actually, there we go. I was just showing some other. So basically we've got, water, barren, forest, shrubland, planted or cultivated. I kind of tried to identify some of these hayfields. And then wetlands and developed, right, which are pretty much just limited to these buildings here. So after grabbing these and generating my random points, extracting the raster values from my two rasters, being this classification classes and the difference, then kind of had a bunch of data to play with and show some statistics. So if I open this back up, and let's look at this is showing density plots for each of my classified areas or classifications, and it confirms my hypothesis, which was that barren, shrubland, wetlands type areas actually have a much lower average, right? So we would want that average to be 0, the difference between the digital terrain model and the bare earth to be 0, as well as a lower variance. Developed, right? So those buildings are getting, significantly misestimated compared with the LiDAR. And then also, forested areas and water, right, have our higher variance and averages. So just running, a statistical test and ANOVA, we've got a p-value of 0, and the comparison between the F statistics shows that, right, there is correlation between the classification and the difference between the rasters. So kind of circling back on, what I was trying to find out through this analysis and present today is that using these drones for surveying, the application really depends on, the land cover classification as well as some other variables, right? But if you've got an area that is primarily, planted or barren or, has low vegetation, the accuracy of your product will vary accordingly, right? If it's densely vegetated, then I wouldn't trust those vertical accuracies in particular. This is a distribution, again, of just the entire data set, so of that entire raster. Again, fairly normal distribution, just meaning that most of the points are represented within, that one standard deviation. The mean, right, this is all the sample points, so it's not necessarily reflected or identical to the other histogram, which was just for the entire raster. In case you're noticing, some discrepancies in those figures. But having, that standard deviation less than 1 indicates a tighter grouping, and in general is good. It means we don't have just like massive outliers, right? And if I want to go back in real quick and just take a look at these profiles again, because it is pretty interesting to compare the difference between all of these. And I think I am running a little low on time, but we should be all right. Just take a look at these. So if I pop open my profiles lines and select that, analysis. Oh, I'm lost. There we go. From layer, profiles, and apply. There we go. Close some of these. All right, there we go. So this is the profile for this line in particular. I'm actually going to change and look at a different one. So let's take a look at this one that crosses the river, actually. And apply that. Okay. And right now I've got the ground specified as, my bare earth model. So again, you see, 0 return or pretty much no data as it's crossing the river, and then a pretty, noisy, or you're able to see like pretty minute terrain fluctuations as it's crossing that other little channel, right? And then we've got, going over bare earth, and there's a little building right there. If I switch this, the ground surface to my digital terrain model and run this again, now you can see we've got higher value crossing the river, more significant, more pronounced dip when we cross that little channel, and then kind of a smoothed out but still higher elevation profile as we go over that little shed building there. There's a few others that I want to get into, but I think I've only got 2 minutes left, so I'll go ahead and open this up to questions. Please let me know, and I'll hop on the Whova chat as well. Thank you.
Hey there, Max. This is Sam. Thank you so much for presenting. Maybe if we could do one question, and the other 2, I think, that you have in the queue, we could answer through the online, and then we'll have the next presenter come up.
Okay, so first question, when those 2D images with geotags are exported, can they be imported or stitched in ArcGIS Pro independently of the control points, or does that depend on the type of drone and how the images were collected? Those 2D images with geotags can be stitched together without ground control points. I don't believe that that's, you can stitch those stills together in ArcGIS Pro as a mosaic if they're, geo-referenced appropriately, but I think that's the benefit of drone to map, is that it's computing a lot more tie points than you would normally get with, just creating an ortho mosaic, right? But you do not need ground control points. It will just affect the absolute accuracy. So, the accuracy of the model or imagery in relationship to the surface of the Earth.
Awesome. Thank you so much. If you could answer those 2 other questions, I think, in the chat or the Q&A would be awesome. And thank you for presenting today.
Yeah, thank you, Sam. It was a pleasure. What type of receiver do you use for ground control? I have used a Leica Xeno 20 in the past. These ground control points were shot by a surveying and architecture company that were using a Trimble receiver with a base station or a mobile rover. I don't remember the exact model, but generally speaking, go for centimeter, sub-centimeter accuracy there, and it'll really improve the accuracy of your outputs.
Sorry, I'm going to have you answer the last question if you could type it in, and then I'll end the webinar so we can get our next presenter on. Thank you so much. I'm so sorry. Bye.
No problem. Take care.